In this presentation, we address a deceptively simple question that can silently break terminal performance. How do you name every yard location so humans and systems can find containers quickly and correctly? A naming convention is not just a label. It is an operational interface between the physical yard and the terminal operating system. We will show why inconsistent naming creates real delays and errors, then build a tiered solution, a complete constraint-based baseline, a deployable greedy heuristic, and a genetic algorithm for global optimization when objectives conflict. The goal is to design a consistent yard location naming scheme. Operationally, the identifiers must be unique and unambiguous, fast for humans to recognize, resistant to common errors, and scalable when the yard expands or overflow areas are activated. A good naming convention reduces search time, reduces mispulls, improves data quality in the terminal operating system, and makes training new staff easier. Without a standard, the same physical hierarchy can be encoded in multiple inconsistent ways. That inconsistency shows up as daily operational symptoms. Drivers waste time searching for containers. Databases accumulate duplicate and orphaned locations, and the yard sees mispulls followed by rehandling. These are not small errors. They propagate into delays, higher equipment moves, and loss of trust in the system. We ground the problem in a realistic terminal. Pacific Gateway Terminal operates a container yard of about 45 hectares and handles over 2.5 million 20-foot equivalent units annually. The yard contains 8,500 ground storage positions, organized across 12 blocks. With inconsistent conventions, drivers spend an average of 4.2 minutes per container searching for the correct storage position. The information system has over 800 duplicate location entries and 1,200 orphaned containers with invalid codes. Retrieval operations suffer from a 12% error rate. A viable naming convention must satisfy several hard requirements. It must be deterministic, meaning the same physical location always maps to the same identifier. It must be invertible, meaning you can decode the identifier back into block, row, position, and tier. It must also be robust to human error, with high dissimilarity so two different locations do not look similar at a glance. Finally, it must have bounded length for labels and scanners, and it must be extensible so new blocks and temporary overflow areas can be added without breaking existing codes. The physical structure is a hierarchy. At the top is the block, which is the macro region of the yard. Inside each block are rows. Inside rows are positions, sometimes called bays. At each position are tiers, which represent stack levels. A naming system compresses this hierarchy into a compact string that both humans and machines can parse. If any level is ambiguous, the whole system becomes fragile. Naming is not just a formatting choice. It is a constrained design problem with trade-offs. You want short codes, but short codes reduce information density. You want distinct codes, but systematic structure can create similarity. You want human comprehension, but machine parsing needs consistency. The right design satisfies constraints and optimizes usability under real operational pressure. We use a tiered approach. Tier 1 provides a full mathematical formulation as a constraint satisfaction and assignment problem. Tier 2 provides a greedy hierarchical heuristic that is deterministic and deployable. Tier 3 uses a genetic algorithm for global optimization when you need to balance multiple objectives such as length, error resistance, and pattern consistency. Tier 1 remains the correctness baseline for feasibility. Tier 1 formulates naming as a constraint satisfaction problem. We define the sets of blocks, rows, positions, and tiers, and we define the candidate identifiers that can be assigned. The key is to represent the problem so every physical location gets exactly one identifier, and every identifier is used at most once while also enforcing length and dissimilarity rules. The sets represent the yard geometry. You have a set of blocks. For each block, you have a set of rows. For each row, you have a set of positions. For each position, you have a set of tiers. This structured definition is what makes the model scalable. It also ensures your naming scheme remains consistent even when blocks have different shapes. Parameters include the maximum allowed identifier length and the minimum dissimilarity required between any two identifiers. We also include weights that define how much we penalize long identifiers, how much we penalize similarity between identifiers, and how much we value making frequently accessed locations easier to encode and recognize. The main decision is an assignment choice. Which identifier is assigned to which physical location? You can also track derived quantities such as the string length of each identifier and the dissimilarity between pairs of identifiers. In operational terms, the decision variables are the blueprint for the labeling system the yard will actually use. The objective balances multiple costs. It penalizes overly long identifiers because long identifiers slow human recognition. It penalizes identifiers that are too similar because similarity increases misreads and mispicks. It can also include an access frequency term so locations that are accessed more often do not carry needlessly complex identifiers. Feasibility is enforced through a small set of hard constraints. Every location must receive exactly one identifier. Every identifier must be used at most once. Identifier length must not exceed the maximum. Dissimilarity must be at least the minimum threshold. This slide exists to prevent omission. In real projects, leaving out one constraint is how you get a naming scheme that looks elegant but fails in operations. Unique assignment means each physical location gets exactly one code. This prevents missing locations and ensures the yard management system never has to guess what a code means. Unique identifier means the same code cannot be assigned to two different locations. This prevents collisions that create duplicate database entries and confusion in dispatch and retrieval. The maximum length constraint prevents identifiers from growing until they become impractical on labels, handheld scanners, and human radio communication. Bounded length is also important for consistent user interface display in the terminal operating system. Minimum dissimilarity means two different identifiers must be different enough that a single slip or a quick glance is less likely to turn one location into another. This directly targets human error patterns, such as transposed digits, missing separators, and confusingly similar codes. This visualization illustrates the hierarchical structure you want the code to represent: block, row, position, then tier. A strong scheme makes each level visible. It should be obvious where the block ends and the row begins, and so on, which is why separators and zero padding often help. This slide explains what good means in the objective. A length penalty discourages long codes. A similarity penalty discourages confusing codes. An access cost term encourages simpler codes where the yard touches the location most often. Even if you deploy a heuristic, Tier 1 tells you what trade-offs the heuristic should approximate. Consider a simplified yard with 2 blocks, 3 rows per block, 4 positions per row, and 2 tiers per position. That creates 48 total locations. A readable naming format is block, row, position, tier with separators, such as block-row, -position, -tier. In this example, all identifiers are unique, length is bounded, and the minimum dissimilarity target can be checked systematically. For block A and row 1, sample identifiers include A-01-01-1 and A-01-01-2, and so on for each position and tier. The takeaway is that hierarchical codes are readable and parsable. When a driver reads the code, they can immediately infer the physical hierarchy, instead of memorizing an arbitrary number. Tier 2 builds identifiers incrementally across the hierarchy. You choose a stable block coding, then define row coding, then position coding, then tier coding. The heuristic prioritizes readability and uniqueness, and it resolves conflicts when two candidate codes would collide. This makes Tier 2 deterministic and suitable for immediate rollout. Typical practical choices include stable block coding such as A, B, C, or zero-padded block numbers. Rows and positions are often zero-padded, like 0, 1, 0, 2, and so on. Separators are kept fixed to help parsing, and conflict resolution rules are defined so expansion does not create ambiguous codes. The flow is pre-process yard geometry, generate candidate codes systematically, check constraints, resolve conflicts, and output a validated naming table. In practice, you also produce a validation function that blocks invalid codes at data entry so the terminal operating system does not accumulate orphaned containers. This code section defines the yard geometry input and the configuration choices for block, row, position, and tier formatting. It also defines the validation logic that ensures the same physical location always maps to the same code. This part generates candidate codes in hierarchical order. It applies separators and zero padding and checks for collisions. The key operational point is that generation must be repeatable. If the same yard layout produces different codes across runs, the system is not deterministic. This section implements conflict resolution when two generated identifiers would collide or violate dissimilarity rules. Conflict resolution should be rule-based and logged, so you can explain why a specific location received a specific final identifier. This part outputs the final mapping table that links each physical location to its identifier. It is also where you can generate additional artifacts, such as barcode label templates and import files for the terminal operating system. This section includes testing and metrics such as average identifier length, minimum edit distance, and a readability score. These metrics help you validate that the heuristic did not create a fragile scheme that will fail under peak pressure. This example configuration demonstrates how to handle multiple blocks with different row counts and position densities. The purpose is to show that the scheme scales beyond a uniform grid. This section continues the example setup and shows how formatting choices, such as separators and zero padding, affect the final identifiers. It also illustrates how you reserve a namespace for expansion, so new blocks can be integrated without renaming old blocks. In the example output, total locations are 1,896. Average identifier length is 8. The minimum edit distance is 1, and the readability score is 95.2%. The operational interpretation is that the scheme is short enough to communicate, consistent enough to parse, and systematic enough to train, while still preserving uniqueness. In a terminal operating system or warehouse management system integration, you should enforce validation at data entry, reserve namespace for expansion, and version identifiers if the schema changes. You should also log and reconcile invalid or orphaned identifiers because the naming scheme only works if the database stays clean. Tier 3 uses a genetic algorithm to optimize naming conventions across multiple objectives. Each individual encodes a complete naming scheme, and selection, crossover, and mutation explore alternatives. This tier is useful when you want to improve global metrics such as minimum edit distance or pattern consistency without making identifiers longer than necessary. The fitness function combines multiple scores, a uniqueness penalty, an average length score, a minimum edit distance score, and a pattern consistency score. Weighting these components defines your strategy. For example, if error resistance is critical, you weigh minimum distance more heavily. Representation defines how a naming scheme is encoded as a chromosome. A common approach encodes block, row, position, and tier components for every location. The representation must preserve feasibility during decoding, so the algorithm does not waste time exploring invalid naming schemes. Operators include selection, crossover, and mutation. Crossover mixes two naming schemes. Mutation introduces small random changes to escape local optima. Operator design matters because you want changes that make semantic sense, not random edits that destroy the hierarchical pattern. This slide highlights each fitness component and why it matters. Uniqueness prevents collisions, length affects speed, minimum edit distance reduces confusion, and pattern consistency improves training and comprehension. Together, these components define what better means for a naming convention. The genetic algorithm process is initialize a population of naming schemes, evaluate fitness, select better schemes, apply crossover and mutation, and iterate. Over generations, the algorithm aims to improve global trade-offs, such as increasing edit distance without increasing length. This code section defines the chromosome encoding and the decoding procedure that turns a chromosome into a naming table. Decoding must enforce uniqueness and length constraints so that fitness evaluation is meaningful. This section defines the fitness evaluation, including how to measure minimum edit distance and pattern consistency. It also defines penalties for violations so infeasible schemes are not selected. This part implements selection and crossover. It chooses parents based on fitness and mixes their components to create candidate children. A good crossover preserves the hierarchical structure rather than producing chaotic codes. This section implements mutation, introducing small controlled changes. Mutation is essential for exploration, but it must be constrained so it does not break the interpretability of the naming scheme. This final code section typically includes convergence logging and output generation for the best naming scheme found. Operationally, you want not just the best scheme, but also evidence that the scheme is robust and not a random one-off. This example run shows the algorithm improving fitness over generations. You track best fitness and observe where improvement plateaus. The plateau can indicate you need different mutation rates, different weights, or a different representation. This continuation shows the final optimized scheme and sample identifiers. The goal is to demonstrate that the algorithm improves global objectives while maintaining feasibility and consistent formatting. Example results include 3,276 locations optimized, 90 generations executed, and a final fitness of 4,167.23. Uniqueness is 100%. The operational takeaway is that global optimization can improve quality metrics at scale. Tier 1 gives the correctness baseline. Tier 2 gives fast, deterministic deployment. Tier 3 improves global objectives at higher compute cost. The typical key performance indicators are average identifier length, minimum distance, readability score, and conflict rate. Tier 2 is best when you need immediate rollout and the yard evolves frequently. It produces systematic codes quickly and can be integrated into the terminal operating system with validation. Tier 3 is best when multiple objectives conflict. You can run optimization offline, and you want a portfolio of candidate schemes to choose from.